Here, I'm just going to show you some tools that I would play around with in class that I think are useful. In particular, one tool. This is from Cornell, the Cornell Neurobiology and Biology Department. They have this really interesting simulation. They actually have a full tutorial. If you click this link, I'm going to try to record my screen while I play around with it. But if you click that link, there's a kind of cool tutorials. They actually have the Hawk Dove game that is going to be the subject of our next set of slides there, and some other things that might be useful. But the game simulator is what you want, and it's really sort of the cool thing that shows you what happens in these other games. It at least provides a visualization of what's going on. So I think it's super cool. One thing to be aware of is uses that methodology of you only put in the role player payoffs. If you remember from the start of the first set of slides, you can do things by only putting the role player payoffs. Like for example, putting in 3, 0, 3, 2 captures all the necessary information about that game. Since it's symmetric, you don't need to worry about putting in both payoffs in each section. So it might be a bit paused. You might have to skip to the next slide. I'm not sure how well this will fit in, but I'm going to do some screen recording and put that in there. Okay, this is the pop-up you get if you click on Game Simulator in that original window that I linked you to. I'm not going to show you my full screen because I want to blow this up. It pops up and it gives you some information at the start. You actually don't need to do much with this. I'll call it red and blue since we're going to do those games that I have at the bottom of this slide. Variables, you don't need to do anything with that. That might be useful when we do Hawk Dove stuff. That would be if you're going to do something like the general form that we've done where the variables are A, B, C, D, something like that. But I don't think we need to do that right now. Let me make this window a little bit bigger. For some reason it starts a little smaller. So you've got this cool little visualization. What it's doing is it's showing you as you move from left to right generations. This little black number that's showing up here when I have my mouse over it tells you what generation you're in and what's happening to the proportion that are red and that are blue. So this initial setup is, well, you're starting initial with 100 red and 100 blue, 50% each, and their payoffs are all 0. In fact, this tells you red against red is 0, red against blue is 0, blue against red is 0, right? And so that's just going to stay 50-50 forever. But if we try to use the first of these games that I have down, where red against red is 3, red against blue is 0, blue against red is 3, and blue against blue is 2. If you go back and review your slides, what you will find is that red is not ESS, but blue is. And the way we can test that is, to test if red is ESS, let's look at a population that's very, very heavily red and has a blue mutant. So let's go with maybe 100 red, 1 blue. Not much to see there, right? 500 generations. Let's expand this out a little more. Aha, right? You can play with these. You can go as far as you need to. The reality is that it might take some time for it to happen, for the blue to take over. Like, the red is not stable. Remember, we said the blue mutants will do better than reds in this. This is one of the first examples we had. Right? If you look at the payoffs, blue does equally well against red as red does, but then if blue ever meets a mutant, it's 2. Well, it's a very slow takeoff, right? Because blue only has an advantage when it meets another blue. When we meet a red, it's the same payoff for each. And at the start, there's very, very few blues. So that advantage the blue has never gets to take off. You're mostly meeting reds, and so they're reproducing at the same rate. If you look down in this corner, that tells you the actual percentage that are red and that are blue. And it's slowly ticking up. And then at some point in time, it starts to really accelerate. We get to a point now where, it's 10-ish% blue. Now it's not unlikely that you might meet a blue, and that's where the blues have a distinct advantage. They do much better when they meet another blue than a red does when it meets a blue. And they take off. And then you go to eventually 100% blue, no red. What about the opposite? So we said blue was ESS. The way we would test that would be, let's go with 100 blue, 1 red, and show that the red, right, starts off somewhere back here is close to 1% and then goes to 0. Right? You don't even need that many generations to show that. The red's, 1% and then down to 0. as you move across. So it's useful for showing that type of thing. Let's try the other game here. So, and the other thing this can tell us is, like, even if you were 50-50, the blues do so much better, right? This is a situation where no matter what, if you have a world of reds and you introduce a blue, or you come any point in the middle, it's going to end up all blue. The blues are just a more fit morph or type in this game. So the second game that I have down at the bottom of the screen is a game in which, when we did it on our own, we found that both red and blue were ESS. So let's look at that. 2, 0, 1, 6. So both red and blue are ESS. So first, it looks like blue is doing pretty well. Let's check blue is ESS, right? If we start with a lot of blue and we introduce a red mutant, the red mutant goes to 0. If you look down at these numbers out here, the red is 0. What if we start with a lot of red and one blue? The blue goes to 0. As we move out here, we're going totally out of blue. And again, there's tiny, you can see a tiny hint of blue there, and then it disappears. But look at these numbers. They tell you exactly what's going on. Okay. Now, there is, if you solve for a mixed strategy Nash equilibrium here, there is one somewhere, right? So it's obviously not this. There will be a point that it's perfectly stable. So it's fewer blues than this. So somewhere around, I bet it's 1/7, which is like 14.7%. So let's try this. 100, 700, nope, 600. Yeah. So if you solve that and try to solve for a mixed strategy Nash equilibrium, you will get 1/7 blue, 6/7 red as the mixed strategy. In fact, we have that on the slides. If you go back to the slides, 1/7, 6/7 as the tipping point. But that's not stable, right? If you introduce an extra red there, it goes off to being all red. And if you introduce an extra blue, it goes off to being all blue. That's not a stable point, okay? That's in contrast to the Dungfly one, which is what I'm going to show next. So I'm actually going to change my names back to short, long weight. You don't have to do that, but why not? So short weight is getting the red color, long weight is getting the blue color. And our payoffs were short against short was 2, short against long was 2, long against short was 5, and long against long was 1. And you can see already, like, look at where we're getting to. We're getting to 0.25 short, 0.75 long, 25% short, 75% long. So what this says is, first, start with, we checked this, but, is all red ESS? No, right? If you have all red and you choose a blue mutant, the blues will take off, but not unlimited. It doesn't become all blue. It stops when it gets to this 25-75 mix. Same thing will happen if you start with all blue and you have a red mutant. The reds will take off, but only in a limited fashion until they get to this point, 25% short weight, 75% long weight. And that's true no matter what your initial proportions are. You will always end up at this mix. So let's start at that mix, right? So that might be 100 short weighting, 300 long weighting. So 75% are long, 25% are short. We're stable. It just never changes. It moves along. Let's throw in some extra short weighting as a mutation. It does not take off, right? If you perturb this, you nudge it a little bit, it doesn't take off. So this is a really cool tool, I think, for visualizing what's going on here. You may have situations where it takes a really, really long time for a slight advantage. If I make this, like in the first one, 6, 5, 6, 6, and you start with that red, it might take, I guess it eventually happens, right? But like, it's not short weight and long weight, it's red. That's like one where it's similar to the first one, where red is not ESS, but blue is. But it takes so long because blue only has the tiniest of advantages. In fact, do that. Oh my God. Now blue only has a slight, tiny advantage. It takes until 7,500 generations. What if I make that blue advantage even smaller? It takes 20,000 generations for the blues to take off, right? Evolution is slow. It takes a long time. You're more likely to see it. That's why people who study evolution study things like flies and stuff, where you can get a lot of generations, or bacteria, where you can get a lot of generations very, very rapidly. This is why we're concerned about things like, viruses are not actually technically alive, but viruses or bacteria can mutate, and that mutation can spread relatively quickly because they're reproducing. Their generations are happening so quickly. The last thing to look at with this, I guess, let's just look at briefly a 3x3. They use red, blue, and green for them, and do the rock, paper, scissors idea. Let's start, hang on, let me just put these at 0 and have even numbers of each, and have, so red against blue, let's have red beat blue but lose to green. So red beats blue, loses to green. Blue loses to red, right? If red beats blue, blue loses to red, and blue beats green. Green beats red, loses to blue. It's rock, paper, scissors. The mixed strategy Nash equilibrium is a third, a third, a third. Look at that. That's wacky. When you throw it off a little bit, it gets really unstable. Some of these 3x3 games are not totally stable. It does on average in here, like these numbers are bouncing around rapidly. On average, it's a third, a third, a third. But what's happening is you're cycling. You're getting like these little things where in one generation there's a ton of blues. And then who does well against blue? Red. So in the next generation there'll be a ton of red. I don't know if I can move the mouse slowly enough to show that. 796. Where's there a lot of blues? Let's see. There's a lot of blues here. 34.66% blue, 32.7% red. The red should start taking off as the blues go down. Yeah, and it goes up to 33. It goes red, and then greens will do well. It'll wave back and forth. So it's not a stable situation. There is no stable point. You would expect 1/3, 1/3, 1/3 on average, but it's not super stable. All right, so this is a fun game thing to play around with. Again, I would encourage you to mess around with it with some of these games and just sort of change payoffs, see what happens. Use it as a tool. Let me see here.